Hey guys, this is Einar. I hope that you're doing great today and welcome to this tutorial where we are going to be conducting a one-sided hypothesis test using the t-distribution. Now the formula for the test variable that we're going to be using is pretty much the same one we've been using so far. We're still measuring the same thing, the difference between a sample and a population mean. And as before, this population mean here is true. It's a true population average. So we're not going to have to take any uncertainty into account in this case. But for our sample mean, we have to take the fact that we haven't asked everyone in the population into account. So we're going to divide this whole thing by the uncertainty of our sample, which is the standard deviation divided by the square root of n. Right, so that's what we're doing. And this part is called the standard error, which is shown in this formula here. The t-distribution, it looks like this. Basically, a t-distribution has a lot of the same characteristics as the normal distribution, except that if you imagine a normal distribution would look something like this. The difference is that we're pushing this normal distribution down, we're increasing the size of our tails, increasing the probabilities out in our tails, and increasing, therefore, the uncertainty. Now, the t-distribution is especially adapted for small samples, so it will change its appearance according to our sample size. The larger our sample is, the more normal the t-distribution will be. It will go towards normality as our sample size increases, i.e. as our n increases. Now, specific for this tutorial is that we're conducting a one-sided hypothesis test. We're not taking this side of the curve into account. We're just looking at assuming that our critical test variable will end up somewhere here in the negative, which affects the critical values that we can use for our different confidence levels. But you'll see more about that later. We're going to take a quick look at our data. We have a sample here. It seems pretty small, and we have a population. And this population, see how this is everyone living in a village, and this village is close to a nuclear power plant. This is their attitude towards nuclear power. So 100 is they really love nuclear power, 0 is they really hate nuclear power. So that's what we're measuring here. And then something happens. The nuclear power plant, the Fukushima nuclear power plant, in which they live close by to, explodes. Okay, so the whole village is burnt to the ground, everybody's scattered all over the place, and somehow we managed to get a random sample, miraculously. Because we're so awesome statisticians, we managed to get a random sample. And now we think that, I think that their attitude is going to be more negative towards nuclear power after the explosion, but we should test this empirically. So we ask people about their attitude towards nuclear power after the explosion. And this is the results that we get. So the first thing we're going to do is we're going to look at our sample size, partly because we're going to be using it in our formulas a lot, because it's part of the uncertainty associated with estimating a mean when you're not asking everyone, and partly because we want to know if our sample is small enough for it to be necessary for us to use the t-distribution formula. So I'm going to count my number of observations. There we go. And I get that we have 20 observations in a sample, and this is small. The benchmark sometimes is referred to as 30. When you have under 30 observations, you should use the t-distribution. Our estimate, i.e. the average attitude towards nuclear power after the explosion, is equal to 65. Okay, so this is an indication. Already now we can see that this number is smaller than that number, so they seem to be less positively inclined towards nuclear power, right? Well, can we be sure about this? No, we can't, because we haven't asked everyone. This is the population size and this is our sample size. So there are loads of people we haven't asked. We might have been unlucky. Maybe we got a sample consisting of a lot of people who were negative towards nuclear power. Is this difference, the question we're really asking is this difference between these two due to random variation? Is it just a random, because we haven't asked everyone? Well, what we have to do is take the uncertainty into account. So we're going to calculate our standard deviation, which is the variation around our estimate. And I choose my data set like so. And I find that we get a standard deviation of 18. So we have the n and we have our standard deviation. These two components make up our uncertainty, and we're going to summarize them in the standard error, which is this part of the formula right there. So I'm going to write equal to the standard deviation divided by the square root of n. Like so, and I get 4. So I took the standard deviation, I divided it by the square root of n. Incidentally, this is part of this formula, so now we're actually ready to calculate the test variable. But before we do that, I want to make one thing really clear. As I mentioned before, the appearance of the t-distribution changes depending on our sample size, and more specifically it's going to change depending on the number of degrees of freedom that we have. And that's kind of a little bit too advanced for this course, so I suggest you, if you're really curious, just Google it and read up on it. But the degrees of freedom anyway are equal to the sample size minus 1, so we have 19 degrees of freedom. This is important because when you're looking up the critical t-values in the tables, you have to make sure that you're looking in the right part of the table because it's divided up by the number of degrees of freedom that you have. Now I've already looked up these critical t-values, so these are critical t-values in a t-distribution based on 19 degrees of freedom. Okay, so we know that now, and we're ready to calculate our test variable. So I write equal to, we want the difference between the sample and the population mean, because that's the change that we're investigating. So I'm taking my sample here minus the population mean, and I'm going to divide that by my standard error, which I calculated there. So the difference between the sample and the population mean divided by the standard error, which is right there. Okay, so I get a critical test variable with a value of minus 2.47. So if we just take a quick look here at our t-distribution formula, minus 2.47, it's somewhere around there. So we're pretty far out in the tail. You know, there seems to be a significant difference. The question is, though, how sure can we be? I mean, is this far enough? How far is this far enough out in the tails for us to be sure that the difference isn't just due to randomness? Well, that is going to depend on our confidence level. So what you do is you determine the confidence level, and we're going to be doing it for 99% and 95%. So in 99% confidence level, I look up in the tables and I find a critical t-value of minus 2.54. So in that case, I will be located somewhere around here. Oh, in fact, I even have the line there. And that means that at 99% confidence, I only have 1% here out in the tail. Now what this means in practice is that if I conducted my test 100 times, I would get a sample mean located somewhere in below this critical t-value. So if I calculated the test variable for each sample, I would get a test variable value that was below this critical, that was above this critical value, i.e. to the right. So what we're looking for is, where is our critical test variable located? If it is located out here in the tail, we're saying we're sure enough that there is a difference, that there's a statistically significant difference, because the chance that this is different in that case is just due to randomness is 1 out of 100, which is a low enough chance for us to say that, okay, we're sure. Even though there is a 1 out of 100 chance that in fact it's just due to randomness, but you can never be completely sure. You have to, set your benchmark somewhere. So the question we ask ourselves is our test variable smaller than this critical value? Well, let's look. Minus 2.47 is not below, because it's negative, we're moving towards a negative, it's not below 2.54. So in that case, we're actually not out in the tail. We can't say that at 99% confidence level there is a significant change because we are located below. I mean, we're located to the right of our critical test value. So I'm going to accept the null hypothesis and say it's true, because this number is not smaller than that number. But then again, 99% confidence level is a pretty high confidence level, right? So we could lower to 95%. This is actually acceptable in many social science studies, and in that case, the critical value is minus 1.73. Is our test variable smaller than that? Well, yes. Minus 2.47 is smaller than 1.73. So 2.47, which is located there, is smaller than 1.73, which is located somewhere around here. Then we are in the tail. So then we can actually refute the null hypothesis and say that yes, there has occurred a change, but not at the 99% confidence level, only at the 95% confidence level. So we're just saying, yes, there seems to be a difference, but we can't be really sure, we can just be pretty sure. And this is a pretty good confidence level to be located at too. I mean, this means that if I conducted my sample 100 times, in 95 out of these times I would get a critical t-value based on those samples that were to the right, I mean higher than this value, but I didn't, I got a smaller value. So The chance is 5 out of 100 that this is due to randomness, and the rest of the chance is that there has occurred a real change. So what we're saying is that we can refute the null hypothesis at the 95% confidence level. And basically that's how you conduct a one-sided hypothesis test using the t-distribution. I encourage you to experiment with this. Try changing the sample size, just write in some of your own numbers there and change the degrees of freedom. Look at how the critical t-values change. Try changing the data so you can refute the null hypothesis at this confidence level. Have some fun with this, and I hope to see you in the next tutorial. Have a really great day, guys. Bye bye.